Okay, so it's a great pleasure to welcome Professor Koji Maruyama, who's going to talk on system identification under limited access with minimal pre-knowledge. Okay.
Well, thank you, John, and then thank you for all arrangement for my stay here. And I'm very happy to have a chance here to talk about our stuff, which is quite new actually. It's about it's one of our work on system identification towards quantum control, because for controlling any quantum system, we have to know first is the dynamics, the details of the dynamics inside the system, which is usually Hamiltonian. So I'm going to talk about how to identify the Hamiltonian inside a big system with a limited access to it. So here are some just rough flow of my talk. So after introduction, well, just the basic things. Hamiltonian tomography of HS, it's just about the basic idea of the identification. And then the third thing is the equivalence class, which is induced due to the limited access to the system. And I'm going to talk about mainly on this equivalent class today. And then next, the actual protocol for the tomography of HSE. Well, HSE represents the Hamiltonian between S and E. Well, it's also governing the dynamics inside E. And then, as a final remark, I'll just briefly mention the controls issues of E, a big system, through a small system S. Okay. So usually, the motivation is we want to make use of a big environment. Well, environment is usually a monoline entity for our quantum control, because it's infinite dimensional, and then everything we do on a small system, the information leaks out to the environment and then it never comes back. So it's really a bad thing, so we want to avoid it, but so this doesn't seem to work. But so okay, if it was really infinitely large, we can't do many things probably. I don't have any rigorous proof about that statement, but we get rid of this assumption about the infinite dimensionality, and then we put just a small assumption, which is okay, the finite dimensionality of the environment. Well, by environment, we mean just surrounding system symbolically, but it doesn't really mean the real environment. So it might be some just large system around a small system S, which is the subject of our control. And then realistically, it might be hard to imagine such a system in the real physical systems. But if this E system, which is quite large already, might be surrounded by the real environment here, E prime, and then this is the real one, so this is infinitely large. But in a small time scale we consider for the purpose of quantum control, this might be regarded as a finite system. So that's the situation we will consider. And then we want to identify what this is just by controlling a small system S. Okay, so this is a physical example we have in our mind of such a situation. So here, at the center of this picture, there's a superconducting qubit, and then this white stuff on it is a diamond with NV centers in it. And then there are loads of NV centers in this diamond coupled with this superconducting qubit. So according to this paper, there were, I didn't make a notice, so there were roughly 10 to the 7 spins interacting with the qubit here. And then what we can control is only this superconducting qubit at the center. So in this case, so our S corresponds to this flux qubit, superconducting qubit, and then E is the bunch of NV centers in a diamond. So it sounds very ambitious, but still it might be nice if you can control this many spins in E system through such a small device. Okay. And then again, so this is just a repetition of the motivation. So we want to identify the internal dynamics and also the interaction between S and E just by accessing, manipulating S. So far, we have obtained some partial results on such a problem. Well, I've been working with Daniel, sitting there, mainly on identification problem for spin systems, spin networks, spin chain, and also not only spin, we have worked on some general network consisting of fermions or bosons. But in these cases, we assume some a priori knowledge about the entire system, such as we know the network configuration somehow, or the type of interaction between these elements, such as, or in the case of spins, say XX spin interaction. So those a priori knowledge is indeed useful to make the identification task very efficient. But what if we relax this condition and then literally make it minimal? So, which is just assuming the finite dimensionality of the surrounding system. Okay, but to do that, still we need some assumptions. And then here is the list of those assumptions. Okay, E can be regarded finite. And rho SE, the state S and E, can be initialized, but we don't have to know what it is precisely. So it's okay as far as we can come back to the same state, but which is unknown to us. So this can be done, for example, by thermalizing the entire state, S and E. Thermalizing using the real environment, E prime, surrounding everything here. And also, we'll make use of some ancillary system, A. So this could be quite large in our actual protocol, as I will show later. But anyway, as an assumption, we assume we can have as many ancillary systems as possible. So it can be provided abundantly. And also quantum operations on this side. So because we, by almost definition, we can't touch E directly. So, but on these things, on our hand, can be manipulated and measured at any instance, at will. Okay, so then the main message is this. So it is, well, at first sight, identifying everything here sounds quite formidable. But despite such an intuitive picture, it is indeed possible to identify the Hamiltonian HSE governing the dynamics here. And then I'll show you how this can be done. But one note should be made about what we mean by identification. Because as I talk about it later, soon, there will be some equivalence class which can be, how should I put it? So, because of the limited access, there will be some equivalence class formed by the set of states and Hamiltonians, and even including the dimensionality of the E system. But because those states and Hamiltonians can't be distinguished almost, well, in principle, just by looking at S. So identification of Hamiltonian here can be achieved just by identifying the equivalence class. Because whatever we do on S here, the outcome we'll see on S will not be different as far as we assume the same, the set of Hamiltonian and state in the same equivalence class. Okay. And then we will constructively show how this task can be done by showing the actual protocol. Okay, so now this is the very intuitive, primitive picture of the equivalence class. So this is a room, and then here this guy is confined in this small dark place. And then he's doing some experiment with a magnet here. And then the whole room, the box, is put in some magnetic field, which is provided externally, either by this kind of what do you call it? Just a normal magnet, or electric coil surrounding the room. So whatever he does in this room, he can't distinguish these two situations. And then it doesn't really matter to distinguish these two situations, but because whatever he does, the outcome will be the same. So this is really the same similar situation we'll have in the quantum identification scenario. So this is more like a picture I showed before. So here are systems S and E interacting through HSE, and then again in this situation the same thing. E1 is interacting with S, but here's an extra E2 stuff. But what if E2 is not interacting with E1, and then we can't see what's happening here? Well, this is really trivial because it's disentangled anyway, disconnected with E1 and S system. But still, this is a legitimate Hamiltonian describing the whole system. So in a sense, this is the most primitive example of the states and Hamiltonian in the equivalence class. So they can't be distinguished just by touching this S system.
So do you mean direct sum or tensor product?
So Hamiltonian-wise,
oh, that's the Hamiltonian.
Yeah.
Okay, not the Hilbert.
direct sum. So what we'll see is only confined in subspace. Okay, and then here's the formal definition of the equivalence class. So we denote this way. So set of state, Hamiltonian, and the dimensionality. And well, roughly speaking, they are, well, these two sets are equivalent, being in the same equivalence class, if we cannot distinguish these two scenarios just by looking at the system S and the ancillary system. So gamma 1, gamma 2, these gamma operations are instantaneous ones on S and ancillary system. And whatever we do, if rho S here and rho tilde AS here are the same, then we cannot distinguish them. So we don't have to care about this difference. So this is the formal definition, but as in this definition, you can see in principle, specifying the equivalence class is really hard because we have to try, in principle, we have to try all possible sequences of gammas and also these time sequences. So this, in principle, this involves infinite complexity, but so this is this is what it says. Yeah, it's a hard task, but just by making some assumption, some condition, by imposing some condition, this identification task of equivalence class B will be achieved. So that's what I'm going to show now. So here's the structure we'll aim at. And then, so this shows S, the small system S, like superconducting qubit, is maximally entangled with another ancillary system, A1. And then E, which might be quite big, but it's also maximally entangled with A2, ancillary system on our hand. So A2 should be as big as E system. So this could be a problem, in realistic scenario. So this is only a theoretical situation, and then the purpose of our work is to show the possibility of the identifiability of this kind of big system just by a limited access, limited manipulation through S.
Can I ask a
Yes.
question? So I thought your identification problem was also to identify the initial SE state, but now you're entangling these with other systems. So how does that state?
Yeah, that's a good point. Well, state, as I said, initial state is fixed, but maybe unknown. So we don't have to know what it is, and it's not a subject of identification anyway. So the protocol I will show later is to steer the entire state to this situation, regardless of the initial state. So it's an adaptive protocol towards this state.
Yeah, I just thought your equivalence class was defined in terms of initial state, Hamiltonian, and dimension.
Yes.
And here you're only talking about.
Sorry, yeah, it's a bit confusing point. Yes, but so equivalence class. Any sets in the equivalence class are equivalent for control purposes. But here, it's only for identification. So to make the identification task possible, we have to steer, this is what we found so far. May not be a unique possibility, but this is the state we first have to aim at, regardless of the real initial state. And then we identify the Hamiltonian HSC here, and then start everything for control again. Once we identified HSC, then everything can be possible, including initialization. So the initialization task and then the control task are distinct in a sense. And then we don't care about the precise nature of the initial state for the identification stage. So once we have identified this, and then because we can do everything, we can initialize the whole thing, S and E, and we can get rid of A1 and A2 anymore. And then, because of the equivalence of the true Hamiltonian and what we have identified here through the identification stage, we can do everything, including initialization.
Okay, it might make it become clearer.
Yeah, okay. And then, so we will call this situation ME condition. So, well, ME obviously stands for maximally entangled, but it doesn't really mean anything significant here. So SC, roughly speaking, SC and A are maximally entangled in this kind of entanglement structure. And then, because we are not allowed to access E system, this has to be checked by accessing A system and S. And then, in terms of what we can see through S and A, this is described like this. So rho S, the reduced density matrix rho AS, can be a maximally entangled stage between A1 and S, tensor, projector on A2 system. Okay. And then, another thing I forgot to mention is we assume everything is kept pure from the beginning. So if it was not, then we can just put extra environmental system to purify it. So just by satisfying this condition, we can take it for granted that the entire system is in this structure. Okay, and then here is a good one for the identification of the equivalence class. So instead of trying all possible manipulations on S and A, this says we only have to observe the time evolution, natural time evolution of S and A. So we don't have to manipulate S and A at hand. So this is a good news because we don't have to consider the infinite complexity of the identification procedure. Well, this direction, so this is not, this is trivial because by definition of the equivalence class, whatever we do, this is the same. This was the definition. But the other direction is non-trivial. So if the natural time evolution was the same, then is this really guaranteed? That's the question. But as far as the ME condition is satisfied, this is true. And then here's the sketch of the proof. So when the ME condition is satisfied, we can show that there is an operation. Once we have this condition satisfied, and then gamma operation here, and then this represents just a natural time evolution, so it should be precisely e to the minus I h t. So this can be transformed into this form. So there exists an operation gamma prime here, which is applied only on the A system, the ancillary system here. Well, but this is a functional of the rho A at stage, so it's not really, it's, well, I can't think of any good word, but so the satisfaction, the fulfillment of the ME condition is very essential. And then once this is satisfied, and then we can always think of gamma prime, which is applied only on the A system as a function of rho AS. Okay? And this way we can disentangle this operation from SE system. And then by concatenating these operations, and then we can collect all operations at any time together to make a gamma prime applied only at the end of the whole time duration. And then, because we already assumed the equality here, this should be the same as this one in another scenario using another Hamiltonian in the same equivalence class. Then again, using the same relation on the previous slide, we can unravel this gamma prime operation to make it, to put it in the original position, in the time position. Then this means that whatever we do as a sequence of gammas, by only looking at the final state on AS, this equivalence is guaranteed. So once ME condition is satisfied, we can identify, well, just looking at time evolution, the result of time evolution is sufficient to specify the equivalence class. And then the next question is how we can steer the entire stage to the one that satisfies the ME condition. And then this is done constructively. The state steering protocol. So this is the this is to establish entanglement between S and A, SA and E, so that the ME condition is satisfied. And then after that, what we have to do is just identify HSE, just by accessing S and A. Then I'll show you how this can be done. So this is so this is the target state or the state steering protocol. And then the tomography of HASE is this way. And then HSE, the main idea we make use of here is that the very basic property of maximally entangled states. So what is this? Okay, so if we had two pairs of maximally entangled things, and then any unitary applied on one end is equivalent to the unitary transposed applied on the other end. So we use this property to see what's happening between S and E. So unitary operation generated by HSE will be reflected using this equality as a transposed unitary operation on A1 and A2. So instead of, because E can't be directly accessed, we will look at A1 and A2, the dynamics of A side to see what this is. But if we look at only this side, obviously everything is maximally mixed. So it's not that that clear, that trivial. But luckily we can access S as well. So by accessing S and A, the joint system of S and A, we can identify, we can obtain information about HSE matrix. So here's the protocol. So the purpose of the protocol is to increase entanglement between S and a small a, and E and a big A. So as a resource of such a strong entanglement, we provide laws of maximally entangled ancillary pairs. And this shows the first round of the protocol, swapping A1 and S here. And now S is strongly correlated, entangled with A2. And then, we look at this, we group this as a new A, and then by letting it evolve naturally, thanks to the Hamiltonian HSE, some entanglement will be generated between here, and then again put maximal entanglement here, and then we repeat this process, monitoring the state SA very frequently. So at every time instance, we have to do state tomography. So this is far from efficient protocol. This is extremely inefficient, but we don't really care because our purpose is to identify some large system. We don't know anything about it. And then repeating this protocol, we can show, so this ESA, delta ESA can be evaluated just by looking at the state SA. So this is a function of rho SA. And then if, well, this is the definition actually. Once we have tomography rho SA, and then we have rho S, rho A, and then we can evaluate delta ESA as well. And then if this tends to 0, and then we can, well, this actually equation shows rho SE will tend to separate state between S and E, and the S state will be maximally mixed state. It's just a simple arithmetic, so nothing essential in it. And then once this happens, this convergence surely happens because we only consider the finite dimensional system. Then we can have this structure between SA and E to fulfill the ME condition as required. And then now we terminate the protocol and blah blah blah. So we can be sure we have the required the structure we desire. And then once we have reached this iteration, we can identify all matrix elements in the Hamiltonian. As I said, because we now try to identify just a single Hamiltonian in a big equivalence class. So the set of equations we'll obtain at the end of this procedure wouldn't give any unique answers. But anyway, just singling out one possible set of Hamiltonian components is good enough. So this is how it can be done. So prepare the state, well, this one, and then again by state tomography, we observe the time evolution of rho SA, and then fully transform it, and then we get these some frequencies. And then considering the time, Schrödinger equation. So this should obey Schrödinger equation. And then we get these conditions for theta and rhos. And then choosing some A, just random set of bases for Hermitian operators in the algebra. And then representing IS tensor HSE transposed on A side, be a linear combination of these bases. And then we will have the set of equations for Hj, small hj here, but it's not unique, but it's still possible to identify one of them, just representative element. And then that's already good enough as Hamiltonian for the control purpose. And here's the numerical analysis, example of a numerical analysis of a protocol. So for a simple system, as a simple system, we consider this one. So it's a system of 4 spins half. S is located at the center, and then it's interacting with 3 spins surrounding it. And then what we want to do is to identify the Hamiltonian describing this system. Okay, so this is only for, so the network configuration is known for the numerical simulation, but the process itself, the identification task itself, doesn't assume such a configuration. And then a true Hamiltonian is said to be this one, the standard Heisenberg interaction between these spins. And then it looks like this for 4-spin system. And then applying our protocol, establishing maximal entanglement between S and E, and also ancillary system. And then what we can get as an example is this Hamiltonian, and then also this one. So these look very different from the original true Hamiltonian. But if you look at, so this is plot of trace distance between the estimated state by using the estimated Hamiltonian and the true evolution. So this red line represents the trace distance between the true dynamics and the observed, the estimated one. So if you look at SEA, the entire system, then actually what we estimated is very different from the true one. But if our access is limited to SA system, then they are the same. So despite the difference in the appearance of those Hamiltonians, what we actually observe on S system S system, and then ancillary system if you want, they are exactly the same. And then this is another one. They're basically the same thing. But the difference between these two is the dimensionality of the environment. So the equivalence, yes?
So what is the basis in the matrices?
This one?
Yes.
This one is just in spin standard Z basis for Paul, defined by Paulis. But this is just a true Hamiltonian. So this is not the subject of. So we don't need to identify this precisely.
Yeah,
Because
we
don't know.
What is the basis in the matrices? How to read the rows and columns?
For this one,
Yes.
it's like up, starting with up, down, up, down, up, something like that. The standard computational basis.
And the first is the system or?
Yes. So this is numbered 1, 2, 3, 4.
Okay.
And okay, then the point is what I wanted to say is the difference in the equivalence classes. So we can identify how to put it. So equivalence class under similar situations, similar scenario of the limited access has been also analyzed by Daniel and Yuasa in Japan. And then, so they analyzed the unitary equivalence under a similar equation, but a similar situation. But this is quite actually even the premises are different in this scenario. And then what we want to emphasize is, so even the dimensionality of the E system might be different. So in this case, we see only 4-dimensional subsystem in this 3-spin system, which is 8-dimensional. And then in this case, we can see all 8 dimensions in this 3-spin system. So despite these differences, what we observe eventually is the same. And then this is true whatever operations we perform on the S system. So this is just for a quick note. So I think you all know about basic stuff of quantum controllability. So once we have identified the Hamiltonian HSE here, and then obviously we know what we can do on this small system S. So by just calculating the Lie algebra spanned by these guys, we can identify, we can spot what operations are possible and then what space as a whole can be controlled at will. Okay. So here's the summary. So despite the apparent difficulty of the task, so identifying something very big, something unknown, something untouchable through a very small window. And then still, even without assuming any physical properties or configuration in such a system, we can, in principle, identify the dynamics in S and E. And then by identification, we mean it's just to identify the equivalence class. It's unavoidably induced because of the limited access to the entire system. And then the information on the triple here enables us to utilize the surrounding system E as a resource for quantum computing. But not only quantum computing is only one of the possibilities we can have if we can have a full command over the entire system. So this can be applied for any quantum control tasks. So that's about it. Thank you very much.
Thank you. I think we've time for a number of questions.
So it's all unclear to me whether the ancilla for the environment, which you had the environment in an entangled state, is that just a mathematical device, or are you actually assuming that for the protocol which you run, you really do have an ancilla?
Yes.
Yes, which? Yes, what?
Sorry again. Yes, it's only a mathematical, stuff. We don't think this can be implemented physically yet.
No, right. Well, no. So your protocol really does involve an ancilla for the environment.
It does, because the unitary operation on SE is reflected on A side. So we have to look at the evolution on big A.
Okay, so I guess my comment was that does seem pretty unphysical to imagine that you're in a situation where you don't even know the dimension of the environment, and yet you can create a maximally entangled state between it and some other system. So
when we have achieved this state steering protocol, A system might be bigger. Well, in general, it should be bigger than E system.
Well,
but still, we can think of only the support of
okay, all right. But even if you don't even know the dimension of E or the Hamiltonian on E, how you would put that in a maximally entangled state?
Yeah, so that can be done. That can be done monitoring by monitoring the quantity delta E S A, I think, which is a function of the reduced density matrix on S and A. Yeah, so this one. So once this tends to 0, then we can say we put maximal entanglement into the E system. So we now covering the whole E system as far as this Hamiltonian goes.
Right, that's how you would create a...
So this quantity can be monitored only by measuring the state on S and A.
Right.
And then this can be computed accordingly. And then once entanglement between this side and A side is saturated, then this doesn't get increased anymore. So of course we might have to stop our protocol before reaching the real maximum. But as far as the time scale for the control is concerned, this is good enough, to make use of the environment.
Just
Other
to
question?
clarify, so basically you are using the dynamics H as E also to create the entanglement between E and the
Yes.
epsilon?
Yes, that's true.
Okay. There are no further questions. Thank the speaker again.
Thank you.